Good morning to the respected professors, scientists, and students. It's my pleasure to welcome you all to the technical talk series titled TransTech Talk Series, organized by National Transportation Planning and Research Center, NATPAC. Through this technical talk, we aim to provide a platform for the experts in the field of transportation engineering to share their knowledge and expertise with us. These talks will give us insights into the latest developments, emerging trends, and cutting-edge technologies in this field. I would like to express my gratitude to all of you for joining us today. We have a fantastic speaker lined up who will be sharing his valuable insights with us on the topic use of geogrids in concrete pavements. Before we begin, I would like to invite Shri Wilson Casey, Senior Scientist and Scientist in Charge, Highway Engineering Division, NATPAC, to deliver the welcome address. Over to you, sir.
Good morning to all. It is with immense pleasure and a deep sense of pride that I extend a warm welcome to each one of you to the 29th edition of the TransTech series organized by KSCSTE National Transportation Planning and Research Center, NATPAC. At the outset, I take this opportunity to warmly welcome our esteemed chief guest, Professor Muhammad Hadi, our distinguished speaker, colleagues, researchers, students, and all participants who have joined us today, both in person and through virtual platforms. TransTech Talk Series is a flagship initiative of KSCSTE-NATPAC, conceived with the vision of fostering knowledge exchange, promoting innovation, and encouraging interdisciplinary dialogue in the domain of transportation and infrastructure. As a premier research institution dedicated to transportation planning, traffic engineering, highway design, road safety, and sustainable mobility solutions, NATPAC has consistently worked towards bridging the gap between research, policy, and practical implementation. Today's session is especially significant as we explore the topic, use of geogrids in concrete pavements. We are honored to host Professor Muhammad Hadi from the University of Wollongong, Australia, as today's speaker. His distinguished contribution to the field of structural and pavement engineering, coupled with his international research experience, bring tremendous value to this platform. We are confident that the insights he shares today will enrich the knowledge of participant practitioners, researchers, and aspiring professionals alike, contributing to the broader goal of smarter, safer, and more sustainable transportation future. On behalf of KSCSTE-NATPAC, I express our sincere gratitude to Professor Hadi for graciously accepting our invitation and to all of you for your active participation in this knowledge-sharing endeavor. Let us carry forward the spirit of inquiry, collaboration, and innovation as we commence today's section. Thank you, and once again, a very warm welcome to all of you to the talk. Thank you.
Thank you, sir. Without further ado, I would like to invite Dr. Himashri PR, Junior Scientist, Highway Engineering Division, NATPAC, to introduce our distinguished speaker for today's session. Over to you, ma'am.
Thank you, Sukanya. Good morning, everyone. We are truly honored to have with us our distinguished academician and researcher who has made significant contributions to the field of structural engineering, Professor Muhammad Hadi from the University of Wollongong, Australia. Dr. Muhammad Hadi currently serves as a professor in the School of Civil, Mining and Environmental Engineering at the University of Wollongong. With a career spanning decades, Professor Hadi has been at the forefront of innovation in the design, analysis, and rehabilitation of concrete structures with notable expertise in the strengthening of structural elements using advanced materials such as fiber-reinforced polymers and high-performance concrete. His outstanding research contributions are reflected in more than 350 peer-reviewed publications in high-impact SCI index journals with an impressive Scopus H index of 53 and over 9,500 citations. His work has been supported by over $2.5 million in competitive research funding, including prestigious awards like the Australian Research Council Discovery Project. Professor Hadi is not only a prolific researcher, but also a dedicated mentor, having successfully supervised 49 PhD scholars to completion and currently guiding a vibrant research group of 12 doctoral candidates. He is also an inventor with 2 patents and actively contributes to the global research community through his service on editorial boards of leading international journals. In recognition of his professional achievements, he is a fellow of Engineers Australia and Chartered Professional Engineer and holds membership in the prominent international bodies such as American Society of Civil Engineers and International Association for Bridge and Structural Engineering. Today, he will be sharing his insights on a highly relevant and timely topic, use of geogrids in concrete pavements, a subject that bridges cutting-edge research and practical implementation in sustainable and resilient infrastructure. Please join me in extending a warm welcome to Professor Muhammad Hadi. Thank you. Over to you, sir.
Okay, good morning to all of you. Last night, before I went to sleep, I heard the news. My condolences about this air crash. It is very unfortunate. So many people lost their lives. I'm sorry about this. I'll start with a couple of things. Please interrupt me if there is a question or if I didn't make anything clear. Please interrupt me. The work that I'm presenting today was done by my ex-PhD student, Dr. Abbas Al-Haddad. So this is part of his PhD. Abbas finished his PhD and he went back to his home country. The reason you see me having a bit more clothes because it is cold here. It is winter. So this is Wollongong. It is beautiful. It is on the ocean. It is nice. The reason I'm showing you this photo is this. This is lighthouse. So people coming from the north can see this lighthouse, whereas people coming from the south cannot see this lighthouse. So they crush in this rock. So later on, they built this other lighthouse. And now it is all electronics. So there's no need to it. This is Wollongong Beach. It is nice, vibrant. There is also not very far from University of Wollongong. They do hang gliding. And this is Stanwell Park. We are Wollongong. We are just south of Sydney, 80 kilometers south of Sydney. Australia is very, very big. Not as big as India, but it is big with very small population. There is train, and of course there is road. The reason I'm showing you this one, this is the recently built about 10, 20 years ago. And here they used cathodic protection because it is right on the ocean, this road, this bridge. So enough about UOW, University of Wollongong. So I'm going to talk about some background, then Geogrids, experimental program, results, conclusions. I'm going to end the talk, this part of the talk, about another building at UOW, University of Wollongong. And then if time, if you want, if you allow me, I can show you what we use, the design method of rigid pavements based on our host roads. So there has been, we have been using Geogrids for a while. People are using it for different materials. And what is Geogrid? Geogrid, they use it mainly for geomechanics, for earth, retaining earth, and the like. But we are using it, we used it for different purpose. Anyway, what is geogrid? So there is uniaxial geogrid, there is biaxial geogrid, and there is triaxial geogrid. Uniaxial is in one direction, biaxial 2 directions, and triaxial is in 3 directions. So people have used it in beams to reduce the cracks, and they put cyclic loading. So what is triaxial? It has high tensile strength, high corrosion to resistance, and high tensile elongation. And I have to admit, I'm a structural engineer. I don't know much about these things, but we learned. And those geogrids, they call it machine direction, where some ribs will be parallel to the load direction, and cross machine direction, this will be all diagonal. So the photo on the left is machine direction, and the photo on the right is cross machine direction. There are ribs which connect the nodes or the joints. So this is in general the geogrids. So we had samples to test their tensile strength. And these are the dimensions based on the standards that we used at that time, ASTM and European standards. Some results, the distance of those equilateral triangular openings, 36 millimeter internal, average width of ribs, 1.5 millimeters, depth of ribs, again, about 1.55, thickness of nodes, about 4 millimeters, and diameter of nodes, about 10 millimeter. So we always, in our labs, we do tests for concrete, for steel, and the like. But for this one, it is different. So we had to build the jigs, the loading heads, and we used our Instron, which is 50-ton, 500 kilonewton universal testing machine, and it has lots of properties. And we tested those materials, the triaxial geogrids, in 2 directions, in machine direction and in cross machine direction. And these are the tests. So the load per unit width, kilonewton per millimeter. As you expect, the cross machine direction was better because you are relying on the diagonals, not only the rupture load, but also the strain. We did some physical tests, and the elastic modulus is about 2.8 gigapascal. The rupture load, 19 and 26 for the machine and cross machine direction respectively, and the strains, 10 and 13, machine and cross machine respectively. We continued and to look at the effect of geogrid on the concrete specimens under static load. Of course, Dr. Haddad did more work, but I'm showing you part of the work. So it is typical investigation, and about 100 years ago, a gentleman called Westergaard, he came up with equations and based on Winkler foundation, and there were three cases for loading concrete pavements: one corner, one edge, one internal. So this part of the research, we did 6 specimens, 3 unreinforced, 3 reinforced. And we tested them under loading concrete slab, loaded corner, edge, internal. The slabs were 900 by 900 millimeter, and the depth 60 millimeters. We put one layer of this geogrid material, triaxial, at 20 millimeter from the bottom of the slab. The load was circular, 140 millimeter diameter. So all those were easy. And I'll talk about more challenges. Our labs, we have the machines, and of course there are restrictions. I like cyclic, I like thousands of tons of loading, tension, compression, wall. Of course, this is research, so we have to do it within the available time and available resources. So, the subbase. It is easy to, we always do beams, slabs, columns, but here we need to model the subbase. And to do this, we looked at a couple of materials. Before then, we had this formwork, 900 by 900. We put the formwork and then we fastened the geogrids to make sure that it is 20 millimeters from the bottom of the slab. Then we encased all this in a steel base. And of course, we manufacture all these things. So the formwork, all those are manufactured by ourselves. Now, we came up with the subbase. The subbase, we cannot put it on steel, but we need to have something which has similar properties, which is what we call subbase material. The rigid pavement, we call it base, and the layer underneath, we call it subbase. So we looked in the market and we found recycled rubber. And actually we bought it and then we tested it similar to plate loading test to end up with a K, modules of subgrade reaction, to simulate the subbase. And 2 layers, 30 millimeter each of the recycled rubber. This is the subbase, and our base is the concrete slab. Now I want to show you something here. This is after testing, before and after testing. You can see that the geogrid didn't move a lot. So we have reasonable casting. This is the section after the testing. Now, this is 900 by 900. We did a lot of instrumentation. I'm not going to bore you with those, but I'm going just to show you the important stuff. So this is some strain gauges for the corner. These are for the edge, applied loading, the strain gauges, and this is the interior load. You can see there are a lot of strain gauges. So this normal Portland cement concrete, 900 by 900 times 60 thickness. And this is the concrete mix. So in Australia, most of the time, they use fly ash and slag as supplementary material. Indeed, Wollongong, because there is the steel works, so there's always slag. And for the last maybe 60 or 70 years, we use slag in Wollongong for sub-base material, and we use it in concrete as well. And the bleeding was not much. There was slump reasonable, 150. Density of concrete, compressive strength, normal. I mean, usually we use 32. It was about 40, and we do all these tests always. And we tested those, and the first photo on the left is the corner, the edge, and the interior. We put a lot of strain gauges as well as LVDT, linear variable displacement transducers. They act similar to strain gauge, but they are connected to the computer to read and capture the deflections. So we have always two specimens identical except for the geogrid. So the U is the N-reinforced, which is shown in figure A. In figure B, this is the geogrid. And we monitored crack width. When the crack is 2.5 millimeter width, what is the load? And this is on the right-hand side, you can see the N-reinforced and the geopolymer or geogrid crack. And these are on the left-hand side, the deflections. And we continued for the edge. And here you can see there are clearly the cracks are orthogonal to main cracks, and for the unreinforced, but for the reinforced, the cracks were further away. And the last one was the interior. The left-hand side is the unreinforced, the right-hand side is the reinforced. And you can see for the left one, for the unreinforced, it is like punching shear, whereas on the right-hand side, the pattern is different. So you can see the cracks are different here. And this is the load deflection at loaded area, at the loading area. So in all cases, you can see the reinforced one behaved much better than the unreinforced or the plain one. The load, you can see it is 17. This is the maximum for the unreinforced corner, whereas the P here, they applied to cause 2.5 millimeter crack width, 20 kilonewtons. Next one is 21, 24. Last one, 96, 150. And the deflection, as you can see, is also better. And we looked at the fracture energy and the ductility. So from this, we can conclude that the geogrid has some effect and it improves the properties of the concrete slab, concrete pavement. Next, Dr. Abbas, what he did, he looked at the effect of fatigue, and he put geogrids and he applied cyclic loading at 7 hertz, 7 cycles per second. And in this case, I'll show you a bit more. Here we did 150 by 150, beams 150, 150 by 500, cross section 150, 150, length 550, and we placed the geogrids at 55 millimeter from the bottom of the beam. Of course, we put those, and always we put some cylinders for compressive strength. We do flexural strength, we do splitting tensile strength. All those are typical testing, but we do. And here, this is the fatigue, and we applied 4-point bending, and the span was 450, and the geogrids are just over 50 millimeter from the bottom, and we put a notch less than 5 millimeter width to simulate the crack, and its length is 30 millimeters. And we put strain gauge at the top, 13 millimeter from the top, to measure the compression, and we put LVDT at the bottom of the beam to measure the opening of the crack. And we put other LVDTs to check the deflection of the beam. This is the formwork with the geogrids, and the one on the right-hand side, we are putting all this assembly. Again, we built all those to check the deflections. So we will build all those to make sure the measurements are correct. This is the cyclic load, identical, each of them 3 specimens, and you can see 1 layer and 2 layers of geogrid, and the behavior was clearly much better. And this is the repeated 4-point bending, and we did this for about more than 600,000 load repetitions. 600,000 load repetitions, and this is the cumulative number of cycles where the load applied and failure to occur. So bear with me. I mean, from this, it is different material. I'm a civil structural engineer. I use steel and concrete, but this is different material, and it may be of benefit. There is a little bit of increase in strength, but also there are others, like reduction of cracks and the like. I'll just take 2 minutes from your time. This is a building at UOW, University of Wollongong. And it was built about now, I would say 5-10 years ago. So this building, it was built on campus. I visited it. It has an electronic microscope. So this is the reason they don't want any magnetic field. So they built it not using steel. So it's concrete, but it was reinforced with FRP, fiber reinforced polymer. And the grid surrounding this electron microscope was FRP. The grid after it was stainless steel, and the remainder was normal black steel. This is what I'm showing you. This reinforcement is for the piles. And this is actually when I went site visit, these are the columns and the walls. They are all FRP. And these are the slabs. The piles, pile caps, beams, columns, slabs, walls, they are all FRP. You can see this is all FRP. And I visited this, I think it was 1 year ago, and there was no problem. Okay, I will stop sharing and you tell me if you have any questions or if you want me to continue with the second part.
Participants may ask questions. Floor is open for questions.
Please go ahead. I'm happy to answer any questions.
Sir, I have one question. Actually, how do you finalize the position of geogrids in concrete slabs you have constructed?
We screwed it to the walls of the formwork. We screwed it to the walls of the formwork. And later on, there was no problem. We checked and there was no problem.
No, sir, I mean that not fixing the geogrids at the position of that, the height of the geogrids, the placing of geogrids in concrete slabs, no? That's...
Yeah, it was 20 millimeters from the bottom.
In the case of beam, it was 50, no?
It was 50, correct. Why did we choose? Why did we choose this?
Yeah, that's the...
Why did we choose the 50? Yeah, okay. So we didn't want to make it close to the middle, the neutral axis. So it was below for the, it was 60 millimeters for the slabs. So we put it in the bottom, 20 millimeters from the bottom. In general, the rule of thumb that we use, because of the cover, so we put 20 millimeters. 20 millimeters. For the beams where it was fatigue, because the intention was to have those notches, 30 millimeter height, so we left 20 millimeters above the notch, and we placed the geogrids. Did I answer your question?
Yes, sir. Thank you, sir.
Thank you.
Sir, in your laboratory test setup, actually you have used that recycled rubber as the sub base. So is there any standard procedure for that? If so, whether it can be used for flexible pavement also?
In this case, we just looked at Australian standards, OSTRODs, and we looked at modules of subgrade reaction, and basically we assumed reasonable number for modules of subgrade reaction. And then we looked at the market, what's available, and we took the recycled rubber. Can you use it for flexible? The answer is yes, as long as you design something and then you say, okay, this is the material that simulates this CBR or this K, modulus of subgrade reaction. I'm unaware if there's a standard for this. Remember, this is research. Any
Other questions?
Yes, sir, I have a question. So when you're testing slab specimens, whether the specimens are laterally confined?
The slabs?
Yeah.
They were
Okay.
with the steel wall. With the
Okay,
steel.
sir, in practice, but we will not be having that confinement, no? So will it be having an effect on the results?
Yes, they will.
Okay.
Ideally, I wanted to have the walls like springs to prevent the confinement. This is what I wanted to do. To have steel, but then put some springs to allow it to expand laterally. But it was a bit difficult, so we didn't do it. But you are 100% right.
Okay, sir. So my next question is regarding the fatigue test. So what was the, test? The load you are applying in fatigue test.
So
How are you determining that load?
We had, initially we tested them to see about 0.1 of an inch, 2.5 millimeter opening. And then this was the static loading. And then we started with this load as cyclic loading. And then we increased the load and we continued cyclic loading. So this was the idea. So we tested them static, determined the load that will cause 2.5 millimeter crack opening, and then we applied cyclic loading.
Okay, so it's like, the load required for creating the 2.5 mm deformation, that same load you applied or a fraction of that you applied, sir?
We started with that load, so many thousands of cycles, then we increased the load and so forth.
Okay, sir, thank you.
Thank you.
So there is a question in the chat box.
Yes.
It's by Dr. Shalini PN Madam. And she's asking like, so what are the desirable non-destructive testing methods to judge on the effective remaining lifespan of these structural elements you discussed?
Oh, that is the...
In situ non-tops.
Yes, non-destructive, okay. There are many of those, but I don't know which one is the best one. Because, I mean, road pavements are boring. They are just slab on ground. They are boring. There is nothing in it. But once we look at it, it is a concrete slab. It is designed for 40 years. hot weather, cold weather, day, night, rain, no rain. And this concrete, it shrinks, it expands. And then you have underneath, you have the sub-base material, and below it, there are the other materials, other layers. And there is fluctuation of water. There is dry, there is, all those are there. So it becomes really very complicated. So the answer is, I don't know. But about 30 or 40 years ago, there is, do you think placement of geogrids, the depth will affect the efficiency? Yes, it will. I mean, the effect, if you put the geogrids at the top or at the bottom, it will have effect, yes.
So there is another question.
Yes.
Uh,
Whether I have compared it. No, I'll tell you what happened. Basically, one of our colleagues had his geomechanics engineer, and we found this material is there in the labs, so nobody's using it. So this is the reason we used it. It was there in the lab, so we didn't compare. So this is there.
Okay, sir. Like, if you have enough time for the next presentation, you may proceed with that, sir.
Okay. There is, I'll just spend 1 second. We have it used to be called ARB, Australian Road Research Board. Now it is called National Transport Research Organization. National Transport Research Organization. And they did road tests. So it is big machine, and they have all those, the testing for pavement. So it's accelerated loading facilities, ALF, accelerated loading facility, and they can, if you have new type of pavement, they put it there. It is big, but you can change the load, and you can change number of cycles and whatever. So it is called accelerated loading facility of, it used to be called ARB, but now it is, okay. So I apologize. I have another meeting in 15 minutes, so we have time. And let me just go to the, and if it is good you are using the same system as we. So Window Explorer. So let's have this one. Okay, is it clear? Can you see my?
Yes, sir, yes.
Okay, so design of rigid pavement. This is one of my students did this one. And basically he built a program for design of rigid pavements. And the way it is, don't worry about this one. So Ostroads is our design guide. It is all the road authorities in the states of Australia and New Zealand. So it is our transport for New South Wales, Victoria Roads, Queensland, and New Zealand, all those. So we have, probably you have seen this one. It was built 1891 in USA, in Ohio, 1891. So 130 years old, still going. So this is first rigid pavement. And we assume we have subgrade, subbase, and base. And then these are the types of pavements that we follow in Ostroads. And then obviously we are getting more and more use. Australia, we have not only semi-trailers, we have, they call it road train. So it is basically a vehicle, and then there are 3 trailers, and they are very, very heavy. So this is Ostroads. Don't worry about it. So there are a number of methods, but Ostroads uses different way. So these are the classifications of the types of loading: single axis, single tire, and so forth. And this is the design traffic. So there is the average annual daily traffic, then direction factor, percentage of heavy vehicle, and then number of axles per heavy vehicle, and then the accumulation, how much it increases. The design is select pavement type, then shoulder, no shoulder, subbase type, effective CBR, concrete flexural strength, reliability. This is something new, not new, 20 years old, and select trial thickness. And then there are those which is really, really difficult. So you start with axle group, then proportion of the load. Either you go and determine, measure, count the number of loads, or there is guide in Ostroads. And then proportion of axle groups, then expected repetitions, and this is the design traffic. So this is for 130 single axis, single tire, 130 kilonewtons. This is the expected repetitions, the applied load. And then you need to do 2 things. One, fatigue of the slab of the base and erosion of the subbase. And to do this, the 130 and 31144 from the previous table, and you take the 130 multiplied by factor of safety, 1.69, and then you take the allowable load repetitions. You can see it is all lens and logs, and this will give you the fatigue, and you continue with all those. And this will give you the effect of this axial load, 130 kilonewtons. It will cause fatigue of 6%. And then you continue for the erosion of the slab, of the sub base, and you go with all those calculations, and you end up with this, and you repeat all those, and for all 6 types of axles for all loads. And then you do the enforcement, and it is a lot of work. So I had a student who did rigid pave, and it was working until Excel changed the codes and Ostroads changed. So this student came, and this one, and very simple. This is OSPAVE, and you just change project reliability, design traffic, pavement type, pavement structure, and you just play with it, click, and it very, very clever way of doing it. And here, these are the results. And we did some evaluation, and this program is working for the last 20 years. So I will stop now, and I'm more than happy to answer any questions. I hope that I showed you something different and hopefully not boring.
Yeah, participants may ask if there is any question. And so our former director, Dr. Samson Matthews, is also available here. Actually, he was on deputation and he joined NIT Calicut back, National Institute of Technology, Trichy. Samson, sir.
Yeah. Thank you, Professor Hadi, for a wonderful presentation. It was good. Actually, people also enjoyed your the topic and in fairness now. Probably the first one which you are given. Now, whether it is practically possible to implement that one in the field. You have used the 90 centimeter by 90 centimeter slabs you have prepared. But what will be the actual size of the slabs in the field?
The width will be more than 3.5 millimeter, 3.5 meters, and the length,
meters.
yeah, 3.5. And if it is plain, at least about 5 meters. If it is plain, if it is reinforced, fine. Of course.
You use like a 20 centimeter spacing, the above that bottom level, the grade. But in the practical also, it will be the same, or probably it can be at the higher level.
Usually, for pavements, it's about 200 mil. So probably we can put it 50 mil, but I don't know. We need to do more research about this.
Oh, okay, fine. Yeah, I can understand. Thank you. Then you mentioned about the 2-dimensional and 3-dimensional grids.
Yes.
Like a 3-dimensional may be more it will be more effective. But again, like probably changing the positions from the bottom, probably you may get different performances. So that again can be a very good research area. Probably somebody can work on it.
Or if we can make the same performance with few millimeters less thickness, i.e. less
Correct.
concrete, then we are saving money. So it can work.
Yeah, that's good. That is correct. Now, how about this concept in the use of prefabricated slabs? We have a concept in India now to have a small panels, like 1 meter by 1 meter slabs we construct. And maybe for light loading and all, probably we can use that one. Whether have you exercised?
No, but we have used fibers. Steel
Okay.
Steel fibers.
Okay. Yes. Thank you, Professor Hadi. It was a good interaction and a good presentation.
Thank you very much.
Thank you, Huma.
Is there any other questions from participants? So a question in the chat box.
Yes. The second part is easy. I can tell you it is, we cannot use it, Geogrids for this software. And the first part, we wrote this more than 10 years ago. Some people wanted to buy it in Australia. And the student said, I will not give it for free, I'll sell it. But of course, we have to sell it through University of Wollongong. University of Wollongong looked at it and said, no, we cannot because of liability. In case somebody designs the road pavement and something goes wrong, then they will come after University of Wollongong. So unfortunately, our students use it. Our students doing our civil engineering course, they use it, but not anybody else, sorry. Because the student is the copyright holder. Sorry.
Thank you, sir. That was a fascinating talk on use of geogrids in concrete pavements. Now, I would like to invite Shri Jagan Bharat Kumar A, Scientist, Highway Engineering Division, NATPAC, to deliver the vote of thanks.
Good morning, everyone. On behalf of NATPAC and Highway Engineering Division, I take this opportunity to extend our heartfelt gratitude to Professor Mohammad Hadi for his highly insightful and engaging talk today on use of geogrids and concrete slab on ground as a part of our TransTech talk series number 29. So your presentation shed light on critical advancement in concrete slab technology and provided us with a deeper understanding of how Geogrids can enhance slab performance. The clarity with which you explained the complex interaction between the materials, structural behavior, and fatigue resistance was truly commendable. We also deeply honored by the presence of distinguished academician and researcher who joined us online today. I would like to acknowledge and thank Professor Samson Matthew from NIT Trichy for his gracious presence. Your participation added great value to the session, and we are grateful for your continued support, sir. We are pleased to share that this TransTech Talk series witnessed over 51 participants from academia and research organization and industry, reflecting the growing interest in sustainable and advanced pavement technologies. Once again, thank you, Professor Hadi, for sharing your expertise with us, and sincere thanks to all attendees for making this session a success. Thank you all and have a great day.
Thank you very much. Thank you.
Thank you, sir.
Thank you. Thank you all. Now the technical session is over.